or the thermal boundary layer. And because of this, you don't lose any information when you need to interpolate your data, when you don't have a conformal mesh. So you have lots of possibilities to adjust your mesh. You define a global cell size, but at the same time you can specify, you can customize your cell sizes and also the growth rates for different surfaces, for the edges, for volumetric areas, and a lot more. BerlinParis Plus automatically adjusts cell sizes based on the curvature. You can see the curvature right here on these heating coils, and larger cell sizes on these flat surfaces without curvature. And there are smaller cells on these heat coils. BerlinParis Plus also automatically creates a number of cells in between surfaces that are close to each other. So that way you can easily and fast create your computational meshes, but you also have the full control over your mesh so that you can resolve everything that you would like to. The simulation was run for about 700 seconds of real time, and you see that we got an increase of the temperature from ambient to 200 degrees Celsius in about 400 seconds. And after this time, the temperature was lowered in order to maintain our temperature of 200 degrees Celsius. When we have a look at the temperature distribution inside the oven on two sections, one section right here, the other section in this area, which is visualized on the left-hand side. So you can see that the temperatures are very high, close to the heating coils, and we have lower temperatures close to the bread dough, and especially in the wake of the bread dough. You also notice that the temperatures are a lot higher at the heat resistances at the rear of the oven. And when we have a look inside the bread dough, then we see a high temperature gradient from the surface to the inner part. So we can see that we still need quite some time in order to bake our bread. You can also see that at the bottom we don't have a temperature gradient or a very low temperature gradient, which is because we modeled a thermal resistance between the bread dough and the baking tray in order to model baking paper. When we have a look at the temperature probes inside the bread, we first want to have a look at the one located close to the surface at the center, and we see that the temperature is very high over there, and we got a high temperature rise. When we have a look at the temperature probe located in the middle and at the center of the bread dough, we can investigate a very low temperature rise, and this is exactly what we have expected before. In this visualization, you can see different temperatures, temperature averaged over the surface, the volume averaged temperature, and this gives you some information about the quality of the baking. You can also see different temperatures on the baking tray and the bread dough, which is what we expected because of our baking paper. When you run a simulation and you are not satisfied with the results, you can adjust the simulation and run a design exploration study, for instance. Here we conducted a design exploration study with multiple objectives. So after 51 seconds, we wanted to maximize the volume average temperature. The first objective was to maximize this temperature in the air, in the oven cavity. And the second objective was that we wanted to maximize this volume average temperature inside the dough. We had defined a couple of design parameters for the shape, the distance, and the height of the upper heating coils, for the position of the fan's air outlet, because the outlet, the fan doesn't only release the air to the right-hand side and the left-hand side, but we can also switch this around for 90 degrees Celsius and release the air to the top and the bottom. So also the distribution of the thermal output to the heating coils was varied. The methodology we used was a self-learning and adaptive search algorithm, which is best in class, and it intelligently adapts the parameters based on the former simulations in order to get an optimized solution in a very quick time. So let's have a look at the results. You see a plot with a volume average temperature inside the cavity on the x-axis and the volume average temperature inside the dough. So each circle represents one simulation. This is our baseline simulation. And you see that we have some simulations where we got an increased temperature. And all these simulations that are on this curve that you can see right here, these are our best designs, and you can choose what volume average temperature you prefer. So either you want to have a high temperature inside your dough, then you can choose this design, or when you prefer the other, you can choose another design, or you choose a trade-off between these. So when we have a look at this plot right here, then you see all the design parameters with their corresponding lower and upper values. So each line represents one simulation with all the design parameters, and this is a very valuable tool when you want to investigate your relationship of the parameters. So, like when we want to see where our high temperatures in the high dough come from, we can select these simulations that we conducted, and we see that in this case the air that was released by the fan was released to the right hand and left hand side, and when we want to have a look at the maximum temperature inside the cavity, then we can see that the air that was released by the fan was released through the top and the bottom. So there is very valuable information for you to learn more about your geometry. So overall, we got a temperature increase in the interior of the baking oven by 32% when having a look at the first objective, and we got a temperature increase inside the bread dough by 16%. The advantages of running these design explorations are that you don't need to know about optimization, so you can fully concentrate on the simulation results. You only have a short preparation time for your simulations, and you can conduct fast and easy design improvements. And quite frequently, you also observe correlations that are not very not very intuitive, that you wouldn't have thought of before. Further applications can be that you model the entire baking oven, including the fan and cooling of the front glass, or when you are opening your oven door. The second example I want to talk about is the freestanding refrigerator. We wanted to have a closer look at the impact of humidity control. We wanted to see how the temperature stratifies, and also the effect of the fan operation and the depending energy consumption. We ran a transient simulation with conjugated heat transfer, multi-component flow with water and air, and also fluid film, solids. We took into account the energy equation with condensation and evaporation, and this time we modeled the fan using a fan curve to save computational time. We ran two variants, one with a fan deactivated, one with a fan switched off, one with a fan activated and one with a fan deactivated. So we started the simulation shortly after the door was closed. So we had warm air and high humidity that penetrated into the inner. And we started at a quite low temperature of 4 degrees Celsius. Let's have a look at the simulation results. This is the refrigerator, 2 boxes at the bottom, a couple of glass plates, the fan located at the top, 2 boxes in the door, and the cooling area at the back of the door of the refrigerator. So when we have a look at the version with the active fan, we see that we have a higher evaporation rate, so that our humidity was transported out of the refrigerator much faster. Also, in the case of the activated fan simulation, we kept a much lower temperature, whereas the temperature rose over time in the conventional refrigerator. We had a quite high power consumption when the fan was turned on compared to the other simulation. You can see this right here. When the fan was activated, we have a quite smooth temperature distribution. The temperature is quite low, but with the deactivated flow, deactivated fan, we have real temperature stratification. We have higher temperatures, much higher temperatures at the top of the refrigerator, and this also indicates that we have very high temperature, very high power consumption when we activate the fan. So you have quite a few advantages when running simulations for your refrigerators. You can even simulate your entire appliances when you want to couple Star CCM Plus with software packages like Amazon. You can have a closer look when you want to when you want to measure the determination of the energy consumption. You can also model the cooling circuit with multi-phase flow and model the impact of the insulating material. And when you have customers that want much better refrigerators, then you can even run studies where you predict the film formation on surfaces. And you can also run the refrigerators with a humidity control in vegetable compartments. So that you can exactly predict the formation of the temperature layers or even gain a unit temperature in your appliance through the use of the fan. So that was my part of the presentation, and I hand over to Christian.
Thank you, Christoph, for that presentation. I think, Jay, you're handing me the controls, right? I think I got it.
Yes, you should have the ball.
Okay, I'm sharing my PowerPoint. Please let me know when you can see a mannequin opening a door of a refrigerator oven.
You're good to go, Christian. Thank you.
Thank you. Thank you so much. Okay, thanks everybody for your attention so far and attending our webinar. I will have another 10 to 15 minutes on some more examples that we run with StarSystem Plus and how it fits into the big picture of our design exploration as well. One example here, keeping with the ovens, or going back to the ovens that Christoph was already talking about. Here would be another example of how a simulation in this field would be of interest. For example, when you open a door and the heat comes out. So one thing, of course, is the comfort for the client, or also he takes maybe a risk for the user, the patient, the user of the operator of the device. And the other thing is, what's important here is we're using a technology that is not very commonly used in other software tools. It's called overset mesh, where we have a mesh, a computational mesh generated around that door that slides then through an interpolation scheme through the surrounding door, and I'll bring that up more often, since there's a lot of motion in those simulations that we have or that we see in appliances and tools, specifically in white goods and kitchen appliances. Another aspect here that I want to mention is it's not just the comfort of the user in front of this oven, but it's important for a design engineer to see if I change my design in any which way, are there any negative side effects? So you might not be able to do much here. If you open the oven door, it's going to be hot, but you don't want to make it worse in case you change anything in the sensoring or some sort of materials inside the oven. So always a quick check. If you have a digital twin copy, a model that you want to simply modify or run through design iterations, check if your design deteriorates the behavior of something that's already out in the field. It's something you never want to do, provide a device equipment to your users and clients that is not superior to your previous equipment. Let's look at another example, an oven model. Here's more a commercial application for a Thanksgiving turkey baking oven, where you have a turkey that rotates and slides. I hope you can see my mouse here, through two walls that are basically heating up the turkey. We're throwing all the physics here again together, like we did in Christoph's oven. We look at the convection, so temperature convecting from the oven to the turkey, radiation from the hot walls to the turkey, and then conduction inside of the turkey again, like we did with the bread. And again, we want to use the overset mesh here to demonstrate how this can be done in a more commercial environment. And the next slide, you can see this. And then with this example, I want to explain a little bit the overset mesh technology. As you can see, you have a mesh that's body fitted to the turkey here, and then has an outer boundary where it interpolates with the main mesh, they call it, that it can slide through. It's called Chimera overset mesh. On the right-hand side, you can see how the turkey heats up. So we want it baked in the center, crisp on the outside, but getting through this process as quick as possible because we are in a commercial environment. So that was to the oven models and specifically the overset mesh. Another cooking example where you use another technology that I want to mention, and I think Christian mentioned it in his introduction, that we also solve for particle flows. And in this example here, we solve for the cooking of vegetables in hot water and a hot liquid. And we use the discrete element model. So in this case, we have particles that we can give very random shapes that you can see on the right-hand side, that we resolve them in the flow, and we actually solve the particle interaction and also the particle interaction in two-way flows, or two-way interactions with the liquid. So the liquid can work on the particles, and the particles also impact the liquid. In this case, we have a volume of fluid multi-phase flow for the boiling water. And then we throw in this potatoes and carrots in this case with these discrete element particles. And you can see in the animation how this works with buoyancy-driven flow here, heated flow. Particles bounce around. Potatoes are a little small for my taste, but very impressive simulation with a lot of physics in there and a lot of technology combined into one model to demonstrate the capabilities. Let's move to washing machines. Something I would like to highlight is how we want our clients to go a path from, let's say, walk before you run. On the left-hand side, you can see a very advanced model, a multi-phase model, where you have detergents being sprayed into a washing machine with a very high-end post-processing methodology. But we would like to start simple for our new clients. So in this case, on the right-hand side, again, we use the discrete element model to represent basically clothes in the washer. And we want to look at the contact force between the particles to assess how the cleaning mechanism works, how clean the clothes get, and just look at 3 different basic designs, different sizes and rotational speeds and things like that to understand the contact forces. So one side, the contact force tells you how clean the clothes get. On the other hand, you don't want to tear or shred anything too much. So that'd be something that we start out with and then go to validation with experiments to trust our model to make sure we represent reality. When we're done with that step, we recommend usually to, then you build up more realism into your model. On the left-hand side, now you see a volume of fluids method where you basically have a multi-phase flow where you resolve the interface between the fluid and the air, in this case water and air, to really understand how the sloshing, what happens in the drum while you activate or while you run your washer. And then getting really forward thinking, we have a model on the right-hand side where the user actually stitched together a piece of cloth by discrete element particles. They can actually be stuck together and interact with each other as a construct, essentially. And now they interact with the volume of fluid free surface flow. You see the free surface on the surface, water and air again, and interact with the spinning, rotating device on the bottom with an overset mesh again here to rotate it. So that's when we get to the cases step by step. Start simple, get more advanced, understand the physics, add complexity, and validate as you go. More examples on the washer-dryer side would be filling of detergent to design this detergent container properly. Yeah, most people probably can fill the whole bottle in there, but it was a good demo case. You see again the free surface flow, and you can look at splashing and effects of that when you design this part of it. A lot of applications in the washer-dryer are also, or generally in white goods, have to do with electronics cooling. And there's so much electronic and smart devices in this equipment these days that you make sure that the equipment cooling, the electronics is according to the requirements, but also you have a lot of sensors in the devices, so there's a lot of electronic components in there as well that you need to consider how they interact with the rest of the heat transfer, fluid dynamics, and so forth. And on the bottom, there would be now a flow-through dryer where we really want to highlight the geometric complexity that we can handle with star CCM+. So we modeled completely the flow around this heat exchanger, as you can see it, but even the flow through the fan. In this case, it's actually modeled as a fan completely, not as just a fan curve that you can do as well. And then really when it gets into nitty-gritty, you can see those holes in the drum here, very fine to resolve. So we have specific techniques like a wrapper that you can use to even capture those little details. Let's talk briefly about some applications. Dishwasher, again, highlighting the process, walk before you run. So we take a simple drum that we rotate the inlet with, and then we have a jet hitting a wall. A great example, we measure the wall shear stress and validate that with experiments. I mean, we don't do that, our clients do that, even though we do have test support also at Siemens, so we can also help you with testing. So now that we have this large portfolio at Siemens PLM. So that would help you basically figure out how to look at sensitivities of your model, where to place your sensors for an actual device, and then build up again complexity and let's say in this case with the dishwasher, add dishes to it in different configurations and see how your jets are cleaning the dishes specifically in detail. I want to extend here a little bit into other applications away from Star System Plus. Christoph already mentioned applications like AIMSIM. In this case, we have here a medical cleaning instrument cleaning device from Miele, where we were able to apply our system modeling tool, AIMSIM, to look at all the different parameters that have an effect here, from pressure distribution pipes to all of the valves and vents and also the pumps and other components in there. So that's something that's really great. Well, in many excuse me, during many phases of the design stages, but specifically when you start out and don't even have a CAD design, you put your system model together and look at the aspects that you want to consider, build your model from that, build your designs from that, and go along with your 1D model to refine the setups and even help you with the experiments, and then eventually even couple it with your three-dimensional 3D realism model to allow us to completely set up the bounding and conditions under which this equipment would run. So a lot of complexity you can cover here up front before you start with the design, and then go along with your 1D simulation all the way through the end design. Another area that we didn't address yet was noise. Here's another example of a washer where we were able to reduce the design time and come up with a very early assessment in the development time to avoid and minimize the noise pollution essentially in a washer. And again, very important here to get early in with your simulation in the design process to avoid highly costly changes at the end of the design process when changes become very, very expensive. Let's talk a little bit about refrigerators. Here's one with an opening door, again using overset mesh, and you can see how the cold air is escaping there. This is also a good example of applications that we use in supermarkets where you have the big open refrigerators and you are concerned with the comfort of your customers and clients. Typical applications, as Christoph was highlighting, is really the duct flow rate and the pressure in compartment, the duct inlets, as shown before, and evaporation and other things. But this is just another example of where comfort level comes into place. A little more about refrigerations. I think they're specifically interesting since they're very high, or they're in the eye of the energy consumption. One thing that I read was very interesting, that in the US, 2009, only 3 out of 10 refrigerators actually had the Energy Star. There was a lot to be done at the time. Much improved since then. One big problem is still that in the US, at least, we have these huge refrigerators. I live in California, and in the Central Valley, we had up to 110 degrees Fahrenheit or 45 Celsius. And people put their old refrigerators, the non-efficient one, into the garage where it's really hot. And the trend to the second refrigerator of these big refrigerators is continuing. So really bringing the energy consumption down here is essential. Another aspect is the recycling. So it's not just the HFCs, the refrigerants that we need to recycle and recover, but it's also the whole, everything in the material side of things, the metals, the plastics, the glass, the casing material. So really in the design process, you want to minimize the waste, of course, and material usage, but also look at recycling. And again, simulation here is a great tool to make sure that you still meet your requirements on noise and energy efficiency, etc. Some more examples on refrigeration. I'm going to wrap it up to have time for questions. Again, let's go from simple to more complex. We start with a simple model to look at the defrosting mechanism on the right-hand side. Then we go more detailed when we look the whole solid liquid to gas transformation here in a 3-phase model with a thin film model with more detail in the model. So this is how we build up our complexity again. We can also go the other way around, so we can freeze the ice. Would be interesting to see about the uniformity and bubbles that could be included in ice. So really do not want to affect the clarity of ice. This is pretty complex to model, liquid to solid. where's the nucleation site and so forth. Certainly interesting for makers of refrigerators. Are there areas in a refrigerator where the cooling is or the freezing is not as expected, or even in the cooling side and on the fridge side? So are there effects from the freezer coming over? Maybe is a part of the site freezing up. Looking at temperature alone, of course, will be the first step, an easy step, but if you want to go all the way as a validation, you could use these kind of models. Now I want to talk a bit about StarCCM Plus again. We have 3 releases per year, and just in the latest one, we had another extension of our model. We have about 300 developers working on StarCCM Plus worldwide. And just in the last release, they added another combination of Eulerium multiphase and large-scale interface, which is part of a VOF model simplification to improve wall boiling and dry out model, which is important for evaporators in refrigerators and also boiling water reactors. We put a lot of emphasis on driving our technology forward and listening to our clients with a tool that we have that is called IdeaStorm, where you can enter your requirements, the requests. And also, we pay a lot of attention to validation and verification. So, the example, we are in the medical VNV40 and also in the nuclear side where heat exchangers are very important. And we have a lot of clients in that field on the nuclear side. And we leverage what we learn in other industries in, for example, in the appliances and tools. Let's go back to design exploration just briefly. We had seen this slide before in Christian's presentation. Just an example on how we go from very simple design to very advanced or optimized with this design exploration model of a fan. So this could be in a refrigerator or an oven, as you've seen it simply. And you might probably add an housing to it, but you can see here you basically want to achieve energy reduction in this case, and we achieved here a 55% reduction at the same similar flow rate by just twisting and turning the blades here, starting with a very drastically bad design, of course, but it really highlights on how far you can take it. I want to show a little more interesting example still here. This is borrowed from an underhood pipe flow design, an automotive example, but it would well fit for a washer that you see on the right-hand side for the tube that goes into a pipe. This is a geometric optimization of a duct that goes, basically it's just a connecting duct, and we're interested here in reducing the outlet swirl. I want to come out fairly straight and also maximize the uniformity of the outlet velocity. To do that, we can optimize or change the design here of this pipe by changing the center line locations, the cross-section radii, and also the angle how it comes in. Let me show some animations here. You can see how the changes in the geometry are hard that our optimization tool heats is performing here, and you can see how that affects the swirl that comes out. This is a flow through one of the fixed designs here, just taking one to see the swirl in here happening. And with this optimization and design exploration, we achieved the uniformity increase by 30% and decreased the swirl by 50%. With the tool, of course, there comes a lot of post-processing power that is important to mention. Here, when we look at the outlet swirl over the uniformity, you see there's a threshold. So when suddenly the swirl jumps up, even though uniformity goes up, there is a stop point here where the optimal is reached, where you don't want to go higher, and then your swirl will increase. So there's many more post-processing tools that I don't want to go into detail, but you can see the whole influence factors from one parameter to the other, how all the components and the parameters in the CAD design get impacted. So just one more example. And with my last slide, so we can get to the questions. So I'm going to wrap it up and mention again how our goal is to increase your value with minimal resources or resources required through process automation, so you can really get there fast. That's the area where you will not have a lot of value back, and same with the testing not in the experimental side of things, but the testing for your model, where you need fast computational systems, or maybe scalability of your computations to get there quickly. So you can really spend your time in design exploration, efficient exploration, improve your design, and create quickly again to sensitivity and robustness of designs, and follow this design cycle. With that, I thank you for your attention and give it back to Jay I think we can probably do a few questions. I see there is a lot of them.
Okay, wonderful. Thank you, Christian. I'll go ahead and put you on mute, allow you to take on some water. Superb presentations, gentlemen. Thank you. We covered a great deal of ground. We literally have a few minutes or so. I just want to let everybody know who stayed with us that your questions, you've been sending those into the dedicated Q&A window. Thank you so much. More than likely, we will probably respond to those via email, but we will try and address a few as we go along. Gentlemen, I'm going to go ahead and unmute you all. Christian Huber, first question that came in for yourself. Is it possible to use your simulation approach on steamers, taking into account condensation?
Thank you, Jay. Thank you, Jay. Yes, of course, it is possible. It is possible to carry out multi-phase simulations as well. It will maybe rise the level of computing power you need, but that's more or less all you have to do, and it's doable with Stuff C++. Yes.
Okay, wonderful.
You can
Thank you, Christian.
You can
Please
also
go ahead. My apologies. Please go ahead.
You can also couple your flow with a solid, and so like conduct a fluid solid interaction study, so that you can see the deformation of your pod.
Okay, thank you. My apologies for the interruption there. Christoph, over to yourself as well. Just a sort of a couple here. I'm going to group them together. This individual works for a company that manufactures baking ovens. What would be the benefits of running design exploration studies for us? We're very tight on time, so if you could be brief on that. I do apologize.
Well, you can use different parts of the baking oven that you can run separately, and when you want to have a closer insight into the whole appliance, you can couple all these and run these all together, and you can run your design studies for optimizing your baking ovens, and use either clusters. You can use your own compute resources. You can couple different computers together. You can establish compute resources with different computers that you want to use. There are lots of possibilities. You can run design sweeps for running your performance curves. So you have lots of varieties to automate and optimize your simulations.
Okay, thank you, gentlemen. I do apologize. We are 2 minutes away from close, so thank you to Christian Debus, thank you to Christoph Heining, and of course thank you to Christian Huber. Gentlemen, I do apologize. There's no way we can get through around about 25 or so questions in the time allowed. Just a quick note to attendees, please continue to send in your questions. I will be collating those down, and the panel will be providing answers, and I will be getting those emailed answers over to you over the coming days, so your questions do not go to waste. But unfortunately, we do have to try and keep under an hour on our live events. All attendees will receive a follow-up email from myself containing a link to the recording of today's session. I'm hoping to get that out to you tomorrow morning, WebEx permitting. If you wish to reach out to any of the panel, the best person to contact has been Christian Debus. He's been kind enough to provide his email address. Please feel free to email him. He is the gateway through to everyone else. So it just remains for me to say thank you to the panel, and again apologize for the time constraints, and of course thank you to you all. We do appreciate you giving us an hour or so of your precious engineering time. With that, the session is closed. Goodbye.